So welcome to ARM TechCon and to this first of NXP's presentations today. My name is Andy Beeson and I head up the team within NXP responsible for the LPCXpresso IDE, which is what we're going to spend the large proportion of this presentation talking about. So LPCXpresso itself, as we'll see, is made up of a number of components. We're going to have a few slides to start with, which will just give you a basic overview of the boards and the IDE. And then the majority of this session will actually be spent doing a number of demonstrations showing the IDE in real use. So we'll start off with just giving you a quick overview of some of the functionality and usage, and then concentrate on two of the advanced features within the IDE. First of all, the support for multi-core projects and debugging of some of the MCUs NXP has got, which combine Cortex-M4 and Cortex-M0 CPUs. And then we'll look at some of the advances we've been making in the subject of SWO trace, which is trace functionality on Cortex-M3 and M4 parts that allows us to get various bits of information off the target in real time. So the IDE, well, LPCXpresso ecosystem is basically made up of two main parts. First of all, we've got the boards, so such as the one we've got projected on the start of the desk. So many of them look like this, which are produced in collaboration with a company in Sweden called Embedded Artists. And then we've got the IDE itself, which is our software development toolchain. As part of this, we've also got access into our LPC Open software, which is basically our peripheral drivers, middleware, and examples. And we'll see a bit more about that in a minute. And one of the key things about LPCXpresso is that it is intended for use for evaluation, prototyping, and development. So you can start off by just doing evaluation of an MCU, carry on using the same debug tools, project management, software, right through to your production. It's also not a closed system, so we've not designed LPCXpresso so that it only works with NXP stuff. So we've got a lot of support in there for third-party tool chains, other boards, other vendors' debug probes, and also middleware. And our aim is basically to make it as simple as possible for you to develop solutions around LPC MCUs. The LPCXpresso boards have gone through a number of generations now, and we're now up to version 3 of our design. So the original boards got released back in 2009 and were quite a short stick in shape. We've now moved to a bit more of a larger rectangle. Some of the features on these, so we've got a built-in debug probe. So there's actually two MCUs on the device. So we've got the debug probe MCU down here at the bottom left-hand corner, and then the main target MCU up here. And the debug probe that we've got on here is based on some technology we've got called LPC Link 2, which is available both built into our eval boards and also as a standalone board in its own right. So a Link 2 in standalone form there. Basically, the idea is that you start off by debugging the MCU that's on the board itself, and then once you've got your own hardware, you can change a couple of jumpers and switch to debugging a target MCU on your own board itself. The debug probe firmware is normally for us is Simsys DAP, but we also have a J-Link variant of firmware available. So if you're a fan of Sega's J-Links, you can actually make use of some of their tools with our LPCXpresso boards. Some of the other stuff we've got on board, we've got a tricolor LED, which we'll be seeing in action shortly. And then we've got things like user switches, and we've got multiple expansion options as well, which do vary a little bit between the various boards. But the key ones, perhaps, these days are the Arduino Uno Shield style connectors that we've got on the top and the bottom of the board. So you can take an off-the-shelf Shield, Or NXP has also got its own general purpose shield, so just a little shield which enables you to access things like SD cards, small screen, and so on. All of our boards are provided with our software drivers, so LPC Open, and you can get a lot more information on the boards themselves from the link at the bottom of this slide here. So LPC Open, our array of software drivers and libraries, is basically intended in giving you a driver for each of the various peripherals that exist on a particular MCU, and then at least one meaningful example showing how that driver can actually be used. Wherever possible, it uses common APIs to ease porting of software between device families, and it's thoroughly tested and maintained, so you should have a high level of confidence that you can use this software both for evaluation and in the development of your real product. As part of LPC Open, we also provide various commonly needed third-party and open source software ports. So, for example, for boards where we've got an LCD controller, we're shipping a variant of MWin, so Sega's MWin, the graphics library. There's things like fat filing systems and so on. So basically, you've got the software there needed to get you going, and it's provided in Kyle, IAR, as well as LPCXpresso IDE format projects. So regardless of which IDE you choose to use, you can use LPC Open with it. So the IDE itself then is an enhanced version of Eclipse combined with the open source GCC compilation tools. It's provided for 3 hosts, so Windows, so runs on Windows Vista and later, Mac OS X, so runs on Mac OS 10.8 onwards, and that's what I'm going to actually be demoing on this morning. And we also support Linux, so out of the box we test with Ubuntu and Fedora, although we know that many customers use it on other distributions as well. One of the good things about Xpresso is that it's provided as a single download and installer, so regardless of which host you're using, you download the installer, install it, and everything that you actually need to get going was included as part of that install. And one of the things that we put a huge amount of focus on is making sure that we're adding features to the vanilla Eclipse to make it easy to use for the development of NXP's MCUs. And we'll see some of the examples of that a little bit later on in the demonstration. So we provide 2 license variants. The free edition provides you with a 256 kilobyte download limit when debugging, which for many of our parts is actually more flash than's actually available on them. So this, for many people, is not a restriction. In order to use it, you follow a simple registration process, which is on our LPCware website, and you can get access to our very popular and well-used forums for support. We also offer a professional edition, which removes that download restriction, adds a few bits of trace functionality that we'll talk a bit about later on, provides email support for you from our development team, and for a single seat costs $495. So if any of you want to go away and try LPCXpresso after this presentation, you can actually go and download it from the LPCware website and then basically activate it and you're away. We're now going to move on to the demonstrations that we're going to run. So I've got 3 demos I want to go through. The first of these is just a general overview of the IDE, so you get an idea of what is available and what sort of things you can do. We're then going to look at multi-core. So this is one of the advanced features that we put a lot of effort into within LPCXpresso. And then we're going to do some examples of trace work. So when you actually first start the IDE up, you will normally have a workspace selector dialog pop up. So a workspace is just a collection of directories that contain the projects that you're currently working on. So you can have one workspace and just put all of your project work in there, or you can use a number of workspaces and switch between them. So we can select a default project workspace as we actually come through this dialog. And it's very simple, as we'll see in a few minutes' time, to switch from one workspace to another while we're running. So if we start the workspace up, so the version of LPCXpresso I'm actually running today is a beta version of our next release, which will be coming out later on this year. So the current version is LPCXpresso 7.92. This is a beta of 8.0, and I'll talk a little bit later on about some of the new facilities in this new version. So we've got the IDE started up, and what we've got here is what is known in Eclipse terminology as a perspective. And a perspective is basically just a description of the layout of the screen. So within the perspective, we have a number of views. So those are the actual individual windows that you can see here. And some of those views are actually tabbed together in sequence. So you can actually see here I'm switching between the Project Explorer view, which is the default one in the left, and then there's various views which we'll use during debugging a little bit later on. So the Project Explorer view is where we get access to the projects that we're currently working on. And inside this workspace I've just opened up, I've got two library projects, which are the board and the chip library projects for the LPC Open package for the particular part family I'm using today. And then we've got a Blinky example in here as well. So I can just open that up and see the source files within that actual project. So that's the Project Explorer view. Over here on the right-hand side, we've got the editor view. And by default, when we open up, we actually get a welcome screen displayed, which provides useful links to things like the user guide. So I can actually quickly go in there and display the PDF of the user guide. And the help system also provides online access to the user guide as well. The welcome screen is there by default. You can close it, and you can turn it off by default for your workspace if you don't need it either. But if we actually open up a file, you'll see that the file is opened up in the edit view. I can open up another file. The two files are there displayed in tabs. I can do things like dragging one file to the right and splitting the two things off. So you've got a huge amount of flexibility in how you actually lay things out. I could do things like dragging the register view from there to the right-hand side of the screen as well. So you can basically lay out the screen in as flexible a manner as you actually want, and then set it back to however you want to use it as well. So we've got the editor view. The editor provides things like context coloring. We can obviously do things like selecting automatically new functions to actually put in from those that are available within the workspace. If I wanted to, I could actually add in a for loop around that particular function, and so on. So you've got a lot of flexibility and a lot of power in the editor. So I'll just close that file before I actually do anything with it. No. Down here in the bottom, we then have a number of other views, the most useful ones of which are the console view, which we'll see in action in a moment, and also the problems view. Some of the other views are used during debug, and we'll see those a little bit later on. And then down here in the left-hand side, we've got a particularly important view called the Quick Start panel. So one of the complaints that people often have about Eclipse is that there's a huge amount of power and flexibility at how you get access to things. And so our solution to that is basically to put all of the most commonly used functionality into one view so that you can easily pick from it. So we can create new projects, we can import a project from a zip file, we can launch debug sessions, and so on. But what I'm actually going to do in this particular case is build a project. So what you can actually see going on now is the project was being built, and first of all, the IDE detected the related library projects. So both of the library projects have been built, as you can see here in the console view. And then having built the library projects, we can then build the actual main Blinky project, as you can see here. So we've got a list of the compiler commands that have been used with things like the flags that have been set. We've got the link command down here at the bottom. And then finally, the tools have actually output some details on how big the image that we've built actually is. So we can see how much code and data we've got so that we know how much of our flash and our RAM are going to be consumed on our target. The other useful thing when doing a build is we've got this problems tab here. And inside there, we actually get a list of all of the errors and warnings. So we can select those from the console, but we can also select them from the problems view. So double-clicking on each of those will take us to the actual source line that is triggering that particular warning or error. So we've got a very easy way of jumping to where the problems are in our code when we carry out a build. So having built our project, how do we actually debug it? So debugging, again, with Eclipse can be quite a complicated thing to set up, but we've carried out as much automation in the system as we can, so that for most cases, all you actually need to do is click on the debug button down here. So what I will first of all do is plug in my board. You can see that a number of LEDs have just come on the board. So these are just status lights. They're basically just taking the default values of GPIO at the moment. But if I click on the debug button, the IDE will first of all just check that the project has been built by default. And it then automatically downloaded into the board's debug probe the debug probe firmware that we're actually going to use for this debug session. So that means that by default, the IDE is always downloading the latest version of the debug probe firmware, which means that the two are completely in sync. So having downloaded that, it's then given us a list of the debug probes that have been found in the system. And in this case, it's just the one probe. So I can OK that. And then for the part that we're actually debugging, which is an LPC 4367, which is a part that we've launched this week, we actually need to select what mechanism we're going to actually carry out debugging over. So in the ARM world, we typically have the ability to debug over JTAG or over SWD, where SWD has a number of advantages. In particular, it tends to take up less pins, and it also provides us with the SWO trace functionality we'll be using later on. But for the 4300 family, we actually need to use JTAG if we're going to carry out a multi-core debug session so that we can connect to all the cores. And we'll see that in a bit in action shortly. So for now, I'm just going to select SWD. For most parts, we wouldn't actually need to do that because most parts you will always just debug over SWD. So I've now made my debug connection. You can see at the top we've now got a new view has appeared, which is the debug view. So we can actually see where in the stack frame we actually are within our program code. So I can do the usual sorts of debug steps like step in. And you'll see that the debug frame updates, for example. There's no variables in this case. I can look for my global variables within the program. So for example, if I display system core clock in there, currently it's got the value 0. And what's actually going to happen when I step over this particular function is it's going to go off and read the registers within the outside the MCU and update that system core clock. So if I step over that, you can see that this part is actually running at 204 megahertz. Other bits of functionality we've got within a debug view are things like the register view. So I can see all of the registers in here. So if I just display the program counter, for example, and step out of that function, you'll see that a number of the registers have been updated and color-coded to show that those updates have taken place. Other things that we've got access to, for example, are the peripherals within the system. So we can actually display a peripheral and its registers, and in many cases it will actually be able to display enumerated versions of those registers. And then we can do things like monitor the breakpoints that we've got set in the system. So as you can see, I've clicked on the source code and set a breakpoint. That has appeared in the breakpoint view. I can then disable them temporarily or even just delete them. So for the purposes of this demonstration, I'm now just going to run this. At that point, we've now got the LED blinking on the side of the board. So that is a very basic overview of the standard build a project, debug a project. The other thing you obviously want to do in many cases is create a new project. And again, this is one of the areas where we put a lot of effort into within the LPCXpresso team. So on the Quick Start panel, we have the ability here to create a new project for a wide variety of MCUs. So when I select the new project, the wizard starts running. I can select the part family that I'm interested in. So in this particular case, we're using the LPC 4300. I then open that up and get a list of projects that I'm actually going to be able to create here. In a few minutes' time, we'll go through the multi-core creation. But for now, we're just going to create a Cortex-M4 application. So I open that up. I again get a choice of more wizards that I can choose from. And in this case, I'm just going to create a default LPCXpresso project. So I can now click on Next. I can then give the project a name. I then need to select the particular MCU that I'm using. So this is quite important because it gives the project system a number of pieces of information about the system. So things like the actual MCU that's being used, details the CPU, so which Cortex-M class part it is. It tells me the memory layout of that part. And that's important because we automatically generate all of the linker scripts that are required by the in order to create the project. So, as I said, on this particular board, we've actually got a 4367. So I'll click on Next. That then takes me to the library project creation mechanism. So on this page, we have the ability to select which LPC open package we're actually going to use. So for this family, the chip library that we need is the default one. But the board I'm actually using as a specific board library, and in this case, I'm just going to use the one for the LPCXpresso 4337 board. So I've now selected the library projects this is going to link with. I've then got a number of other pages which I can carry out modifications to the project on, but mostly I can just leave these set to default. I then finally get to a page which allows me to tweak the memory layouts of the project that we're going to create. So for most standard projects, you don't need to touch this. But as we'll see when we come to the multi-core project creation in a minute, this is actually quite an important thing to be able to tweak. So we'll just next that and then click on Finish. And what that has done is it's created a new project with a set of source files in here. So it's got a default startup file, which is correctly configured for the part that we're targeting. And in particular, it's got a file called newproj.c, so it's taken the title from the name of the project that we created, which creates some default code. And in particular, it implements the smallest possible LPC open style project, which just turns a LED on. So it's not doing anything particularly exciting, but it means that we've actually got confirmation if we run this project that all of the linkages to the library projects have been set up correctly, that our hardware is basically working. So what I will do is just build that project. So we can see it's built, and launch another debug session. So again, it will give me the choice of the debug probe to use. And those settings are actually remembered between debug sessions. So once you've connected to a particular part, debug probe for a particular project, it's only if the IDE detects that things in your system have changed that it will prompt you to actually go and re-look for the debug probe. So these are all once-time settings, if you like. So I OK it. Code is downloaded into the flash. And if I now run it, but it does show you that using the project wizard, we have created that standard basic project that we can use for then expanding and developing our own code from. So that's a very quick run through of the basic functionality of the IDE. What we're going to do now is switch workspace. So to do that, I can just select the file menu and go into a workspace where I'm going to carry out some multi-core project creation and debugging. So the IDE restarts, opens up that new workspace. So NXP has got a number of parts which support multi-core targets. So we've got the LPC 4300 family, which some parts of which have got a single Cortex-M4 and a single Cortex-M0. The board that we've got here has got a 4367 part on it, and that's actually got one Cortex-M4 and two Cortex-M0s. So this means you've actually got quite a lot of CPU grunt power within your MCU. And these MCUs run independently from each other, but there's basically an interprocessor communication mechanism set up so that each of the CPUs can trigger interrupts over to the other and basically allow you to coordinate between the CPUs. So quite often we see people using the M4 for carrying out sort of powerful mathematical type calculations, and one of the M0s might be running a simple UI. And the other CPU, the Cortex-M0, can be set up to poke the SGPIO peripheral that we've got on part of these boards, which gives you quite a lot of functionality. You can be actually configured to provide things like additional UARTs or I2C channels. So within the workspace that we've got here, I've actually got a number of projects already set up. So in our previous workspace, we just had a single chip library project and a single board library project. We've now got two. One configured to build for the M4, which is this one here and this one here. And then the ones that are tagged with the -M0 are configured to build for the M0 part. So basically we need to select the appropriate configuration options within the tools in order to build code suitable for running on those. The other projects I've got in here are a multi-core setup. So when we're actually using a multi-core MCU, what LPCXpresso provides is a means of linking a number of projects together. So we effectively have a project for each of the Cortex-M0 parts, which are known as slave processors, and a separate project for the Cortex-M4, which acts as the master project. So what actually happens with each of these projects is that the two M0 projects are built, they are converted into binaries, and then built into the M4 image. And it's actually the M4 that downloads the code into the target and then allows the M0s to be run. And we'll see that taking place in a minute. So I've got a pre-configured project, but what I'm actually going to use is I'm actually going to create a new one, just so you can see how easy this is to actually do. So what we actually need to do is run through the project creation mechanism for each of those CPUs. So first of all, I'm going to create a project for the M0 sub So basically the M0 sub is one of the two M0s that we've got in the system. It's just the name we give it to so that we can tell the two apart. So we'll create a simple LPC open project for that. The process then looks fairly similar until we reach the last page. So I just select the board project, click through next a few times, and then we get the memory layout. So the memory layout that we're seeing by default is the memory layout for the whole MCU. But we actually want to build our M0 sub-project so that it runs from a particular bank of memory on the part. And we've actually got dedicated memory for that particular processor, these two banks that we've got down here at the bottom. So what I'm actually going to do in this case is very simply use the memory configuration editor to delete all the other memory banks. And I can then go next and finish. So what that wizard has actually now done is it's created an LPC open project very similar to the one we had before, which just turns a LED on. It's linked it with those M0 board and chip libraries, but it has also modified the linker script that will be generated to use that memory map that we've just configured. So I'm very quickly going to do exactly the same thing for the M0 app processor. So we again select the LPC open project. Select the right part, so 4367. So the -M0 just tells the tools to configure the code to build for the M0 rather than for an M4. Select the board library again. And again, get to the memory configuration view. And what I'm going to do here is cause the M0 app code to run out of the second bank of flash that we have on this particular part. So what we don't want to have happening is for the code for all three of the cores to be running from the same memory block, because that's obviously going to cause quite a lot of memory contention. So we're going to run the M4 from the first bank of flash, the one M0 from the second bank of flash, and the second M0 from one of the banks of RAM. So I'm just going to delete, well actually I can just swap that block of flash around and also swap that block of RAM around. So that means that our M0 app processor will end up with its code in the flash and it'll use this block of RAM for its data. So I can again just click through next and finish. And that has now built my two M0 projects. So the final stage is just to create an M4 project. So again, we select the LPC OpenC project. I'll just call it M4. Select the part that I'm targeting, so a 4367. Again, select the board library. Click through the next few options. I'm going to leave the memory map to its default. But what I need to do as this final stage is actually create the linkage from the M0 applications to the main M4 project. So I'm going to first of all tell it which project to use as the M0 app. So I can just click on the Browse button and select my project. And I also need to tell the tools that we're going to put that code into the second bank of flash. So that's the M0 app. Again, I need to select the M0 sub. And again, that project is now linked into the main M4. And I can then finish. So what that has now done is basically created 3 link projects. And if I actually build the M4, what will happen is that all of the slave projects will be built. So it builds the 2 slave projects. So if I just select each of those in turn, you can see each project has been built. And then the M4 has linked the binaries from those 2 projects into itself so that they can get downloaded to memory. Now, that particular project is not a very exciting one if I run it, because you basically have 3 cores that all turn the same LED on. So what I'm going to do instead is use this project that I created in exactly the same way a couple of days ago, but I've put some code in it such that each of the 3 cores blink a different LED at a different rate. So what I actually need to do is start off by clicking on debug of the M4 project. And what that will actually do, if we just wait a minute, so I've got to select Seamstress DAP again for the first time. I need to ensure I pick JTAG because we're going to do multi-core debugging. And then at this point, I actually need to tell it which core I'm going to debug. So in this case, I need to select the Cortex M4. So what I'm actually going to do in a minute is I'm going to create 3 connections, all within the same IDE instance. So I will do that almost straight away, in fact. So we've now got into the M4 code, okay? And one of the things that the M4 code contains in it, if I just step through all this initialization code, is these 2 lines down here, which are calls to actually start the M0 slave projects. So when the LPC 4300 comes out of resets, the slave cores are held in reset still until the M4 releases them. And this basically allows the M4 to copy the code into the right memory blocks. So that code is actually generated. So if you see here, we've actually got the code inside this file that actually does that initialization. So that gets created as part of the project creation process. So if I just open up the M4, so this is the project we created 2 minutes ago. You can see the same files created in there. And if I open up the M4.c, you can actually see those 2 lines have automatically been put in by the templates that created the project. So everything is there and ready and waiting for us. So going back to the demo then, what I will do now is I will just connect the debug session for each of the M0s. And you'll actually see we go through the same process for the first time that we connect. So we've actually got 2 M0s. We need to pick the right one. So I happen to know that device 1 is the M0 sub, so I shall select that. And that is not actually, so it's connected, but the processor isn't actually running yet. So I'll just leave that as it is and connect to the M0 app. Again, the first time we do this, we have to select how we're going to connect to it. And what I've got now is all of the actual CPUs connected. So if I go back to my main processor, the M4, and just run most of the way through this. So I'm just going to run to that point there. Yeah, so we got 1 LED on. If I actually now execute, the M0 sub is certainly connected. So you can actually see the code for the M0 sub down here. The M4 is actually still running, so you should be able to see that LED is on. We've now got a LED blinking, yeah. Then my M4 I have just stopped. I can stop my M0 sub as well. And hopefully everything has now stopped doing anything. So I can do things like setting both of the MCUs off to run at the same time. So there's no synchronization between the actual 2 things. But we can do this in hardware, but we can synchronize from the software point of view. So I can set both of those off at the same time. Similarly, if I select both of them, I can pause both of them at the same time. So we've got the ability to synchronize which one is running at a particular point in time. I can also do things like viewing the registers for each core. So at the moment, I've got the M0 sub selected, so we can see the M0's registers here. I can select the M4, I see the M4 registers, but what you really want to be able to do is see both lots of registers at the same time. So what I'm actually going to do is I'm going to create a new view of registers, which is actually opened up down here. So let's just drag it up there so we can see it. And as I switch between the two, you will see that both of them update. But what I can actually do is pin one of them to the M4, which I've done over there. Right, pinned. Select the other one and pin that to the M0. Okay, so we've basically now got both registers updating at the same time. So again, if I run it for a minute and pause it again, we've got the synchronization so that both banks of registers are actually being displayed, so one for each core. And if my connection to the other core had worked, I'd have been able to do that with the 3 registers. That should have worked. If anybody wants to see it afterwards, I will prove it. But that's the basics of multi-core. So you can actually see what we've done is we've added functionality in here to allow those multiple connections to the multiple CPUs within the MCU and debug those all from within that same IDE instance. So what I need to do now is move on, and we're now going to look at some of the trace functionality that we've got inside LPCXpresso. So I'm again going to switch my workspace. I will just do one demo on trace. So SWO trace functionality is something that we've been working on to work with our LPC Link 2 technology for a while now. And the next LPCXpresso 8 release will add support for basically doing printfs and scanfs over the trace channel via a thing called the Instrumentation Trace Macrocell, or ITM. So this is functionality we used to support in our tools in an old life using a different debug probe, but we now have this coming along for use with the LPC Link 2s. So I've basically got a project which does something you normally wouldn't do, which is inside an interrupt handler, it's got a printf routine. And traditionally, when you do printf in the ARM world, that carries out a semi-hosting operation, which typically causes the core to be stopped, data to be transferred from memory by the debug tools, and then displayed in a console within your IDE. And what ITM allows you to do is stream that data directly from the CPU without stopping the core from executing, which means it takes place in real time. It isn't affecting your interrupt handlers and so on. So I should just start a debug session for that particular project. So again, the first time we launch a project, we have to select the debug probe and the debug connection mechanism we're going to use. And so project is connected. So what I have the ability to do now, and actually I'm just going to run through that one function, is turn on various elements of our trace functionality. And in this case, I'm going to turn on the ITM trace. One of the things that this trace mechanism needs to know is the clock frequency that the core is running at, so it can actually synchronize the clock off the debug channel. So we've actually gone and automatically detected that. So I okayed it. And in a second, for some reason, yeah, there we go. We've got a console view as just displayed down here at the bottom. So what I will do is now start executing my program. And of course, what's happened is that my trace hasn't started coming out. So my blinky is blinking. And if I switch to the right console, which I'd failed to do, you can actually see that we're getting a timer tick coming out from that printf inside that interrupt handler. So again, doing a printf inside an interrupt handler, certainly when you're using semi-hosting, is a definite no-no. But what we're doing here is redirecting that through the ITM channel. So the code that actually does that is contained within this project itself. So I've got a very simple piece of code with a few pointers, which implements a function which in our tool chain we call __ syswrite. And basically that is the function that sits underneath printf. So by sending that channel out, it's basically a UART. We're sending it out over the debug channel and displaying it here in real time in the tools. So I'm just going to stop that. Just to prove there is other trace functionality in the system, I will just turn on the profile view. This isn't going to be very exciting because there's not a lot going on in this program. But this is one of the other elements of functionality that's available today in the released version of LPCXpresso. Okay, so I'm afraid that brings me to the end of my presentation. Thank you very much for your attendance today. I hope it's been interesting.